Today, we will be talking about lasers. In general, when people think about lasers, they think about narrow beams of light, sometimes weaponized or destructive and blow things up. This is because of how popular culture present lasers, for example, as a weapon on a TIE fighter from Star Wars, shown in the image. This isn't wrong, however, but what people don't realize is that there is more to lasers than just blowing up starfighters. In this video, we will be talking about the science behind laser technology, how lasers function the way they do, what a laser instrument is made of, and some scientific applications of lasers that don't involve fighting a galactic war. So what exactly is a laser? According to Encyclopedia Britannica, a laser is defined as a device that stimulates atoms or molecules to emit light at particular wavelengths and amplifies that light, typically producing a very narrow beam of radiation. Breaking that down into more simple terms, a laser is in fact a narrow beam of light. But it's not just any light, it's light at a specific wavelength. Now what does that mean? Well, looking at this electromagnetic spectrum, we see that visible light has a range of wavelengths, going from 400 nanometers to 700 nanometers. So white light we see, like sunlight, is in fact light from several wavelengths of the spectrum. A laser, however, is light from only one, or a very narrow range of wavelengths, which is why when you see a laser, it only shines one color. How does a laser only emit light from a narrow range of wavelengths? Let me give you a hint. Laser is an acronym, short for light amplification by stimulated emission of radiation. As the full name would suggest, a laser emits light at specific wavelengths based on the principle of stimulated emission. In stimulated emission, a photon is incident on the electrons at a higher excited state. In our figure shown, this is the E2 level. The photon causes the electrons to regress back to a lower energy state, E1, while emitting photons that have similar properties that are in phase with respect to time with the incident photon. The second part of the definition was that a laser amplifies the coherent light. When there are more electrons in the excited state than the lower energy state, also known as population inversion, the incident photon causes all of the electrons to revert to a lower energy state, causing an equal amount of coherent protons to be emitted along with the incident photons, resulting in a greater intensity of light. So more electrons equals a greater amplification of light. For a laser, the stimulated emission occurs from one set of atomic energy levels, resulting in an emission of light at a specific wavelength. On the device, there are two mirrors, parallel to the back and front edge of the device. The mirror on the back is 100% reflective, so all light incident on the mirror, emitted through stimulated emission, will be reflected back. The mirror on the front of the device is only 99% reflective, where only 99% of incident light is reflected, and 1% of incident light passes through the mirror. This 1% of light is emitted out the instrument, and that is what we observe as a laser. To put this in perspective, it's like the retro video game Pong, where the light bounces between the mirrors. The difference is that the front mirror lets 1% of the metaphorical ball through, and the light keeps bouncing back and forth. An important thing to keep in mind is that the mirrors must be parallel to one another, and the stimulated light has to travel directly perpendicular to the mirrors, or also hits the edge of the instrument, as shown in some of the arrows in the middle.
There are 5 important parts in a typical laser system. First, the long glass laser tube. Second, mirrors. Third, power supply. Fourth, the water cooling device. And fifth, the gas system. A common glass laser tube has 3 major types of port. Each type of these ports has 2 connections on both sides of the tube. The port that is directly connected to the glass tube is to link with the cooling device. The one that is near the top is to connect with the gas system, and the other one is used to connect with the power supply. Mirrors. Each side of the tube has 1 mirror. One is 100% reflective, and the other one is about 99% reflective, with a small hole in the middle. The power supply. The power supply will connect with both sides of the tube and provide sufficient energy to excite the gas molecules inside the tube. The water cooling system. A simple water cooling system is required as the heat generated by the excited molecules inside the tube may cause a damage of the glassware. This cooling system forms a small closed loop and water circulates inside in one direction. The gas system. The gas system provides gases such as carbon dioxide and helium. This system also connects to both sides of the laser tube. However, it is not a closed loop. Gas molecules enter the laser tube from one end and are removed from the other end by the vacuum pump.
Another very cool application of lasers is called laser cooling, or Doppler cooling, because it uses the Doppler effect. The Doppler effect is what causes a car passing by you to sound like "meow." Essentially, the wavelength of a wave changes depending on how an observer moves relative to the wave source. So, if a particle is moving towards a laser, for example, the particle will see a shorter wavelength or higher energy photon than if the particle was stationary relative to the laser. So, let's say you have a laser that's monochromatic and has energy just below the energy required to electronically excite some gas particle. Now you have a system of the gas, a bunch of the gas particles are in a box and they're bouncing around. Some are moving up, some are moving down, some are moving left, and some are moving right, and any combination thereof. Now, if you shoot a laser into the box, certain particles are going to be moving towards the laser, certain particles are going to be moving away from the laser. So certain particles are going to see a blue shifted laser and certain ones are going to see a red shifted laser, and so on. Now, if you have a particle moving just fast enough towards the laser, it's going to see a laser that's blue shifted, which means it's higher in energy. And therefore, if it's moving at just the right pace, it's going to have, or it's going to come into contact with a photon that's just the right energy to electronically excite that particle. Now, what happens after the particle is excited? Well, it's a collision. The momentum of the system is combined, and since the vectors of the momentums are opposite, the end momentum of the system is going to be lower than the initial momentum. Additionally, the particle is going to eventually relax, and it's going to emit a photon in a random direction. Ultimately, the effect of all this is that the particle that is excited by the laser will have a lower momentum after the absorption and fluorescence than before the absorption and fluorescence. And since temperature is defined as the average kinetic energy of a system, or of particles in a system, as your particles are continually being excited and then relaxing, and every time this occurs, they're lowering their individual kinetic energy, you're going to end up with a lower temperature system because the average kinetic energy of the system decreases by a tiny amount every absorption event, eventually leading to a very, very cold system if you do this enough times.
Laser-induced breakdown spectroscopies is an example of the utilization of laser in order to analyze our wanted sample. This method can analyze gas, liquid, and even solid compounds without alternating or changing the property of the sample. The laser light is emitted to a mirror and reflected into the focusing lens at an angle. This light passes through the lens as an energy source onto the sample. Sample is ionized to form a plasma. The ionized atoms excites and relaxes. When relaxed, light is emitted, then passes through collection lenses and fiber optic cable. The light gets dispersed through the prism onto the sensor, and we get our resulting spectra.